Hello, we are Team 7. Our team members are Jim, Muska, Stevie, and Zhiyang. First, let me introduce the part 1. My name is Zhiyang, and I am in data science program. My undergraduate major is mathematics. My research focuses on large language models, generative AI, and also reinforcement learning. I have 2 year experience in database kernel, specifically in SQL Engine. In part 1, I'm going to talk about the project overview and the progress in employee part. Our project is about developing a grocery store management system. This is a database application project. This is an overview of our system. We use the database to store users' data, and also we have an interface to interact with users. We also have a middle layer to connect database and interface. The middle layer fetch the data from a database and deliver it to interface. We divided our system requirements into 4 parts. They are employee, store manager, customer, and vendor. As introduced in proposal, an employee can be cashier, custodian, and inventory clerk, and stock clerk. We continue the ERD in proposal. This time, we transfer every entity set into tables. We follow the standard transfer procedure, and in employee part, we get 19 tables in total. We also implement normalization on our tables. For example, we need to record which employee maintained which region. So we have a maintenance record table. We add the SSN and the region ID column into this table, but in reality, each employee is responsible for an assigned region, so that SSN to region ID is the functional dependency. Because of this table is not in the third NF, so that it's also not in BCNF. To stop the data redundancy problem, we decompose this table into 2 small tables, maintenance record and maintenance region. We separate the SSN and the region ID into a small table. This time, both these 2 tables are in the BCNF. This is the corresponding changes in ERD design. Our system also need an alert function. When the quantity of a specific commodity runs lower than a user-designed threshold, the system should send out a message to the stock manager. To achieve this automatic read function, we use the DBMS trigger to achieve this. We define update trigger on commodity table and shelf lot table. This is our definition. It's very easy. Just if statement to judge the new tuples the quantity if the new tuples quantity lower than the threshold. If so, the system will insert a tuple into inventory alert table. Here is the brief demonstration. At the beginning, we have a commodity called bread, and the quantity equals to the threshold. So of course, we don't have any alert in alert table. Now someone bought a bread, so the DBMS execute update statement. After the update, the quantity becomes lower than the threshold, and automatically an alert received in inventory alert table. Next, my teammate Steffi is going to talk about the progress in customer part.
Thank you, Ziang. Hello, everyone. I'm Steffi Dorothy. I'm currently pursuing my master's in data science. My undergraduate major was in information technology. My academic interests lie in machine learning, data engineering, and data analytics. I'm particularly interested in exploring how these fields can be applied to solve real-world problems. So in part two, we will look at the customer aspect. I'll cover the steps I took to build a customer database. First, I figured out what customer data we needed and how we'd use it. Then I designed the database visually using ERD. After that, I cleaned up the database to avoid errors. I also added automated actions called triggers, and I'll talk about the problems I solved along the way. First, I would like to discuss the foundational elements that shaped our database design, which is the customer requirements and queries. Starting with customer requirements, I identified the core information we needed to capture. This included essential account information, details related to online orders, a comprehensive order history, and the tracking of returns. These requirements dictated the structure of our customer-related tables, ensuring I captured all necessary data points. Below, I have customer queries. These represent the common actions and information retrieval needs of our customers. This includes the ability to create an account, set up a subscription, search the inventory, and look up their order history. These queries guided our design to ensure efficient data retrieval and a user-friendly experience. Essentially, these requirements and queries formed the blueprint for our customer database, ensuring it met both our data storage needs and the functional requirements of our users. Next, I designed the database. Here, this slide shows how I structure the customer data. On the left side is the simple view, and on the right is the full database design for the customer side. You can also see some icons for features like notifications, subscriptions, and recommendations. In total, I created 22 tables based on this ERD. This slide illustrates the normalization process I undertook to optimize my database structure. On the top left, I initially had an order table with several attributes, including order ID, customer ID, cart details, shipping and order dates, quantity, and order stages. As you can see, while this table met the first and second normal form, it did not satisfy the third or Boyce code normal forms. This indicated potential redundancy and update anomalies. To address this, as shown on the bottom left, I decomposed the order table into separate tables. This decomposition allowed me to achieve all four normal forms, ensuring data integrity and minimizing redundancy. On the right side, you can see the two ERD snippets that visually represent these relationships. These diagrams illustrate how the order, checkout, and cart tables are connected and how the data flows between them. This normalization process was crucial for creating a robust and efficient database, which is essential for the application's performance and reliability. Now, I'll explain the triggers that I created. The first trigger is the update order total. When someone adds or changes an item in their order, the trigger calculates the new total and updates the database. And the flowchart here shows how it works. The next trigger is the reduce commodity quantity trigger, which I implemented to manage our inventory levels. So this trigger is designed to automatically reduce the quantity of items in our commodity store table whenever a new item is added to an order. It is activated after an insert occurs on the order items table, indicating that a new item has been included in an order. So the purpose is to maintain accurate real-time stock levels, ensuring that our inventory reflects the items that have been ordered. The next trigger is the update loyalty points trigger, which I implemented to manage our customer loyalty programs. This trigger automatically updates the loyalty points in the member table whenever a payment is recorded in the paid table. It is activated after an insert occurs in the paid table, signaling that a new payment has been processed. So the purpose of this trigger is to ensure that the customer loyalty points signaling, it basically accurately updates the payment activity. And there's a flowchart again to showcase the trigger's logic. So when a new payment record is inserted into the paid table, the trigger calculates the loyalty points earned, and it uses a predefined formula here. In this case, it's the total price divided by 10. So this calculated value is then used to update the loyalty points field in the member table. And finally, I would like to talk about the challenges we faced. One problem is the data redundancy issues. Initially, we faced a duplication of data entities, which was resolved by implementing 3NF normalization. And the other one was user interface complexity. So designing an intuitive and functional GUI was challenging. And so we simplified the interface by following UX UI practices. And that's it from me. And now I would like to hand it over to James.
Thank you, Steffi, for the handoff. My name is James, and I'm in my second semester of WPI's Master's in Data Science program. A little background on me is I graduated from Boston University with a degree in economics and currently work at Oracle in the Global Analytics Division, where I've been for the last 5 years. My interests in data science cover all the hot topics like ML, AI, LLMs, and even data engineering, which I feel doesn't get enough love. For my part of the presentation, I'm going to spend a little bit less time on the database side and prioritize more of the UI design, our different tool functionalities, and the test cases for checking these different features. So, starting with the database design, this is the part of the ERD which covers the store manager role. In total, there are 11 tables, of which 6 are relationship sets, meaning the other 5 are entity sets. These tables are mainly strong entities. However, we do have a weak entity on the far left of the diagram, shift schedule. Shift schedule has a composite key made up of shift date and the primary key of the employee table, SSN. As this is a weak entity, the relational table has the delete on cascade condition. So if a row is dropped from the employee table, it is subsequently dropped from the shift schedule table as well. This part of the ERD also includes both key and participation constraints to capture the store manager role requirements. The 2 entity sets, budget and store, capture both of these constraints. The bold arrows from budget and store pointing to the store manager represent both a key and participation constraint, as each budget in each store must be managed by exactly one manager. Store manager also has both constraints with the store entity. However, as a manager can have multiple budgets, this is only going to be a participation constraint and not a key constraint, as shown in the diagram. So that's all I'm going to talk about with the ERD. And next, I'd like to move on to our UI design. This is the homepage of our application for the grocery store, the Daily Pip. When designing the UI for our application, we prioritized an intuitive and user-friendly view that would avoid an overly cluttered and messy layout. Taking inspiration from similar web pages, we constructed a navigation bar that lets users jump from different parts of the tool, like shop, deals, sign in, and contact. Additionally, in the top right of the corner, on the top right corner of the web page, there is a profile button that lets the users update their account information as well as explore their order history. Clicking on the shop button will direct you to our inventory search feature. Using the search bar, the user can filter down our commodity table in the database to dynamically update their view. A key element in this design that boosts user friendliness is that the search uses a like statement along with Python code that removes any extra spacing, converts everything to lowercase, meaning the search is not case sensitive and doesn't need an exact match. If there are no results from the search or an item is out of stock according to the inventory table, the page will then display no results found. However, if the user finds what they're looking for, they can specify the quantity and add this to their cart. Creating the cart was for sure a little tricky, especially getting around how to have the tool remember what was in the person's cart, especially if they didn't log in. The way we got around this and overcame this obstacle was to create a specific secret user key for everyone that accesses the tool. This enables the tool to remember what items were added to the cart, even if the user wasn't already logged in through their customer account. So on top of that, even with the secret key, if you head to the home page or somewhere else within the tool, the cart will remain intact. Also, one of the latest features to pass our testing, our user testing, are the remove and clear cart buttons. These buttons do exactly as labeled and can either trim down or empty out your cart entirely. The last part of the UI that I'll showcase is our login page. This page still needs attention and more user testing as the account creation and authentication isn't working just yet. However, the idea is that once a user logs in, they will have access to more functionalities like customer order history and updating their account preferences. Wrapping this all up, this is a table of our test cases and showing what has passed and what has failed. We are currently 3 for 6 and rapidly approaching 4 for 6 as the create new customer account functionality is likely just one extra period or an unexpected indent in the code away from working. As I already previewed, the search, inventory, and add item to the cart functionalities are working. Then for the customer order history and customer recommendations, those are going to be our top priorities, along with continuing the UI development in phase 3. Now I'll hand over the spotlight to Muskan to discuss the vendor role in the ERD before she closes out with our lessons learned and future plans.
Thank you, James, for that wonderful introduction. Hello, everyone. I'm Muskan Mahajan. I'm a master's student in data science. My professional experience include I was a former technical analyst at Tata Consultancy Services, and my interests include machine learning and AI. So the agenda for today is covering progress in the vendor part of the application, lessons learned, conclusion, and future plan. So coming to the vendor requirements, our system needs to handle several key functions related to vendor operations. These include commodities, managing invoices, ensuring quality assurance, and overseeing delivery logistics. Coming to the vendor queries part, the system facilitates essential tasks such as accessing store contracts, updating the contract terms, tracking shipments, and looking up available products online. By streamlining these processes, we aim to enhance efficiency and ensure accurate record keeping. Coming to the ERD database design for the vendor has the main entity as the vendor, which has the primary key as vendor ID. Then we have entities delivery, contract, inventory order, store manager, and commodity. So we have a ternary relationship between inventory order, vendor, and the store manager. And the vendor is directly affiliated to the commodity entity as well, which comes under the employee part. We have implemented normalization in our applications, as mentioned by my teammates as well. So for the vendor normalization, initially, we were creating the vendor entity having primary key as vendor ID and the other attributes as name, phone number, email, address, representative, contract ID, and pricing. So this entity was in first normal form and second normal form, but it did not comply with the third normal form due to transitive dependencies, where vendor ID determined contract ID, which in turn determined pricing. So to address this, we decompose the table into two, vendor table and the contract table. So the vendor table stores the vendor specific details, and the contract table now manages contract details, including pricing, delivery schedules, and validity periods. This decomposition ensures compliance with third normal form as well as the BCNF as well. So this enhances our efficiency and avoids redundancy in the vendor table. So coming to the lessons learned, through this process, we gained valuable hands-on experience in database design, normalization, and query optimization. We implemented SQL automation using stored procedures and triggers, enhancing database efficiency. Our SQL proficiency improved as we integrated the database with a web-based UI, ensuring seamless interactions. We utilized UML and ERD diagrams to structure complex relationships, ensuring data integrity. Additionally, we explored performance tuning techniques to optimize queries, improving overall system efficiency. Beyond technical skills, this project strengthened our problem solving skills, teamwork, and project management abilities, preparing us for real world database challenges. So, to conclude, coming to the close of the second phase of our project, we have successfully normalized our tables to BCNF, converted our ERD into relational tables, developed and tested trigger statements, expanded our UI design by incorporating widgets, and progressing on coding out the application with Flask. From our initial proposal, our goal was to create well-structured tables, resolve errors, and optimize SQL queries. Based on our progress, we have met our expectations and laid a solid foundation for the next phase of development. So just what I mentioned in the conclusion, we have our task table, which we have covered up, which we plan on covering these features in our phase 3 of the project, which is recommendation engine, send inventory alerts, customer review, and member notifications. And based on the timeline that we had provided earlier in the proposal of our project, we have successfully completed the execution halfway in our phase 2, and we plan on completing the UI design in phase 3, which is at 50% currently. And the middle of the project, the middle layer is almost 25% completed as well. And designing test cases and generating test data for the evaluation sector of our timeline is 25% completed as well. So we hope on achieving these targets in phase 3 of our project. Thank you. And these are some of the background materials that we used. And thank you.